Right, welcome everyone to this second edition of the AISB Seminar, held as a webinar on Zoom due to the current situation. And I'm very pleased to welcome with us Kerstin Dautenhahn, who is a fellow of the AISB and has been fellow, I think, since 2018, where she at the AISB convention gave a talk about, well, entitled, "Will the Future Be Bright for Social Robots?" And I guess we're going to hear an update on that today. Kerstin is also an IEEE fellow and holds various accolades from big named societies. She used to work in Hertfordshire, so we were lucky to have her as a plenary speaker at AISB 2018 before she departed the UK for her current job at the University of Waterloo. And before we start with Kerstin, just a look ahead what we're planning for the next seminar. Tony Korn has agreed to give a talk, and hopefully by the end of this month or early in June, we'll be able to schedule the talk from Tony, and I'm also looking forward to that. But for now, we're going to go back to Kerstin, and a very warm welcome, and I'll hand over to Kerstin to give the talk for today.
Hello and good afternoon. Well, at least in the UK, it's afternoon now. So I'm just sharing my screen here. So I hope that you can see it. Yeah, Betty is nodding. So yeah, thank you for the invitation. It's a great pleasure for me again to give this talk. As you've heard, in 2018, I gave a keynote talk at the AISB convention. And now I would like to give an update, and I will primarily also talk about new research projects and results that we got from these projects here at University of Waterloo in Canada. Of course, many of the themes that kept me busy in the UK at University of Hertfordshire, I mean, these themes are still there, but also because of COVID-19, we had to be quite creative over the past 12 months. Let me phrase it like that, because in-person studies since March last year here in Waterloo, we were not able to do any in-person studies. So I will give you some illustrations of the type of things that we could do and that we published about since then. So just to give you an idea, I'm here in a province called Ontario. Ontario is just a very small part of Canada, but is in itself a few times as large as the UK. So I'm surrounded here by some quite nice nature, which due to COVID, I haven't been able to enjoy as much as I wanted to, but well, hopefully things will get better next year. So here in Waterloo, I'm the director of the Social and Intelligent Robotics Research Lab. And just to again remind the audience, what do I mean when I say social robots? So some definitions that have been given are just shown here. So these are typically robots designed to interact with people in human-centric terms and to operate in human environments alongside people. So it's typically a situation where they share space with people. And the human-centric terms refer specifically to them engaging people in an interpersonal manner. So they are communicating with people, they are coordinating with people using verbal, non-verbal, but also affective modalities. And as I've pointed out before, of course, not all robots in the world have to be social. It really depends on the application area and the contact they have with humans. How often do people interact with these robots? For how long? What is the role of the robot, and so on? And this will all influence the requirements on giving these robots social skills, which is very time consuming and requires a lot of effort. So we should only do this when we think this is necessary. Now, one of the things that I've been working on for many years, I mean, I worked in the UK for 21 years, and many of my projects were about companion robots. And these are typically robots that that have certain tasks, so they are not purely, you know, for entertainment. They have certain tasks, they provide certain assistance, but they behave socially, so they carry out these tasks in a socially acceptable manner. And as mentioned, a key to developing social robots for certain application areas that I'm interested in particular, is this human-centered approach, where you go through iterations of prototyping and co-design and experimental testing, and then you repeat. You go back to prototyping and so on. So it is generally very important to get feedback from potential users of the systems, but also other stakeholders around during the whole process, which was of course difficult since March last year. These are just a few of the robots currently in my lab. The iCub is not shown here. It had a day off and sent me apologies that it was not available to take this photo. So people's views of robots and robot cognition is, of course, influenced by a number of factors, not just what people see in the media or in movies, but also due to our tendency to anthropomorphize objects, including robots. So we attribute personality or emotions or goals, even on very non-animate systems. So this short video is just a little reference to the famous experiment done in 1944 by psychologists that shows how people, even when they just see geometrical figures moving around, they interpret their behavior in terms of agents with goals, agents with personalities. And of course, our view of robots, of social robots in particular, is also influenced by what Cherry Turkle calls designs of relational artifacts, robots that are particularly designed to invite people to form a relationship with them. And of course, with reference to Jerome Bruner and many fascinating books he has written about humans, human memory, human thought, the way how we perceive the world, interpret the world, and communicate in narratives. This has also a key impact on the way how we view robots. But there is a wider context, and I've been quite intrigued by this quite simple diagram that I found in the recent introductory book, Human-Robot Interaction, which is highlighting the point that when you talk about human-robot interaction, very often people just talk about the diet. So they talk about the robot, how to design that robot, how to make it social, what social skills should it have. Or they talk about the human user in dyadic interaction. How does the person interact with the robot? How does the person perceive the robot? But there is a wider context, because in real-world applications, you typically have not just one person sharing a space with the robot, you might have several people. So then you talk about also group behavior, teamwork, team behavior among people, also including the robot. Or you might have one person or several persons interacting with a group of robots, which then also entails multi-robot situations where the robots not only interact with people, but also with each other. But I will also illustrate some projects where you need to not just look at these diets or team interaction, but you also need to look at the organization. Where are these systems actually being deployed, and what are the issues if systems are being used without the researchers being present? And finally, the more wider context, the society, the societal level. What does society think about social robots? So I'll go through some examples of research that I've been involved in. So why do we need companion robots? an area I've been interested in basically for most of my academic career is robots as assistants for people with special needs. And here in Canada, like in many other countries, you have the situation that disability is not only having a major impact on people's life as such, but also on their education, on their employment, and it can have a major impact on poverty. So attempts to use assistive technology, including robots, including social robots, can potentially have a major impact here. The other area where currently there's a lot of discussion on using robots is with this envisaged industrial revolution number 5, where the emphasis will be on cooperation between people and machines. So not a scenario where robots are meant to replace people, but where they work alongside human workers, trying to take advantage of what humans are good at and what robots are good at. So this is this area now, when people talk about cobots, this is what they mean: collaborative robots, typically in an industrial context. And also the not only in Canada, this is some data from Canada, but it's similar in the UK and many other countries, the aging population, which has a big impact not only on the national health systems, but also on family caregivers. And here in Canada, for example, you can see here on the right some figures about the amount of unpaid hours of care that family caregivers have provided. And family caregivers are typically people who still need to hold down a job, who often still also have a young family themselves. So this also puts a huge burden on them as individuals, not just the healthcare system as such. So here in Waterloo, we have now also started projects that are currently in progress on healthy aging. So how to support independent living, both in the case of working with people with dementia. So for example, in applications in care home. So this is work that we have not yet published, so I'm not able to go into detail here, but this is basically work I've also been interested in the UK at the University of Hertfordshire, with studies we did in the smart home in the robot house that you can see here. So, so robots need to be social. They need to be socially intelligent in order to also carry out certain tasks, to recognize their users, to distinguish between different types of users, to be able to learn and adapt in these application areas where they, let's say, they provide support for people with special needs. They need to provide encouragement and assistance. But how do we ensure a high level of engagement from the user, or how do we improve the quality of interaction? Since, again, a key point for social robots is if we are not designing the interactions with them in a way that people accept, that they are comfortable with, these systems will just not be used. They are then destined to collect dust in research labs rather than actually being used in the field. So how do you improve the quality of human-robot interaction? There are, of course, many ways that you could look at, in the way how the human behaves, in the way how the human can perceive what the person is doing, activity recognition, for example. But also the robot can have access to how the person feels. So getting access to a person's internal states, vital signs, stress levels. This would allow the robot to adapt and to respond socially to a person's current state. So this is the approach that we take in one of the projects here at University of Waterloo, where we look at physiological signals. So we look at a person's vital signals, and we use a robot in order to give feedback and to adapt to the person's activity in order for these vital signs to stay in a healthy, desirable target range. So, well, that's basically what I just explained. So this is the project that we call HRI PhysioLib. It involves several students and postdocs, and it's primarily also the MSc project of Austin Kotek, who will graduate this coming term. So it's about the development of a software framework to support the integration of physiological adaptation in HRI. So here we look at the dyad as the social unit of interaction. So one robot interacting with one person. So this is the wonderful research team that we have here. So why do people use physiological signals in HRI? They use it, as I mentioned, in order to improve the quality of the interaction, in order to be able to reason about the affective states of humans. You don't necessarily need to use physiological signals. You might also try to infer such data from visual data from cameras. However, research has shown again and again that using visual data alone can suffer from a number of real-world noise issues, but also privacy concerns from end users. So users might be more comfortable attaching a physiological sensor, like commercially available Fitbits, for example, to their wrists, as opposed to having a camera pointing at them and recording everything that they are doing. So generally in psychophysiology, you typically would have a control group and you would have a comparison group. So the comparison group is where you expose people to certain stimuli, for example, to a robot, and you typically have a baseline, and then you have the condition where you evoke certain emotions or you subject people to certain conditions, and then you see how people react by comparing, making comparison between the baseline and the intervention group, or you could just look at without the baseline. You might just look at the intervention and see what type of different signals do you get in these conditions. So what we focus here is in this project is on ECG. Electrocardial signals, basically electrical activity of the heart rate using electrodes placed on the skin. There are also other measures you could use, for example, EMG, which is recording the skeletal muscle electrical activity changes, or you could also use electrodermal activity. So all three are quite popular in the field of HRI, but we focus on the heart rate here. So in particular, one measure that is interesting here are these so-called RRI intervals, which is illustrated here. So it's basically these intervals between these peaks that you can measure, and you can use the heart rate variability in order to infer someone's stress or excitement level, but also exercise performance. And it's exercise performance that we are focusing for the moment in this project. So as I said, quite a few people in the field have already used physiological sensors, but systems being developed, the software frameworks being developed are usually very specific to a particular context, to a particular system, and they are rarely used to create physiologically adaptive behaviors in the social robot, which is our focus here. And a lot of the systems also that are being developed are commercial. And so it's difficult to get access if, from a research perspective, you want to do any modifications. So this is just a very brief overview of the software framework that we have developed. You can see on the right different types of sensors that can be integrated in the system. Then you have a processing module, which is doing signal processing and the feature extraction, which then is then being used by adaptation mechanisms in order to provide real-time adaptation of the robot's feedback to what the person is doing. And finally, this information is then, of course, tightly linked with the robot's expressive behavior. So this can be speech or facial expressions, body movements, and so on. So we are using here LSL, lab streaming layer, to synchronize the physiological data, which that's an approach that we found most useful and flexible in order to allow us to develop this framework that can be interfaced with various types of robots and various types of physiological sensors. So this was really key. We did not want a system that is just very specific to one robot or one type of sensors. We wanted to have this more generic architecture that you can see here. And in the current experiments, we are using commercially available fitness devices, monitoring devices, these polar devices where we can collect ECG data and then compute the heart rate variability. And we developed an app that can also stream those data and visualize this data in real time. So as mentioned, it's important to also use signal processing, since the actual physiological signals are often very, very noisy, and you also need then to extract the relevant features. There are two ways in how to process this data. So you can use heuristic, basically just if-then rules. If you want to tell the robot how to react to certain changes in the person's physiological state. So you could say, if the heart rate variability is in this particular range, then the robot should react in this particular way. So that would be a heuristic approach, but we are also investigating machine learning, probabilistic approaches, which can be used in a complementary way. So we are interfacing the system with different robots that we have in the lab. And we did one use case earlier this year with the robot that you can see in the middle here. It's the QT. This robot is called QT. So this is the decision-making loop of the robot, interface to various controllers, robot controllers, such as the iCub or QT or the Pepper, and using a dedicated interface also in order to monitor and process this information. So this use case that I mentioned is about a physio coach. So the robot is a coach that, given the initial state of the person in a resting state, and collects the data, acquires these signals, then assesses the data to see, is the person within the target state, within the desired healthy physiological state or not. Maybe the person is under-exercised or over-exercised, and this then gives rise to the robot to give certain types of feedback in the way that I just explained, for example, using heuristic rules. So in this use case here, so people are shown both videos of people performing certain exercises, and on the right you can see how we taught a robot in order to perform movements that are also related to the person. Of course, the robot is not as flexible and agile as a human being, but certainly there are certain arm movements and head movements that can indicate to the person the state of the current exercise. So this is just a short video I wanted to show you to give an illustration. So this is when the person starts the exercise at a very slow speed just to get started. Then the robot is encouraging the person to move a little bit faster and to also do different types of these exercises. And when the robot or the system will detect that the person is over-exercised and needs to calm down, slow down a little bit, then the robot will accordingly give some feedback on that. So as I said, so at the moment we are using this framework in particular for the health coach use case, but we are also thinking of applying this later to other applications. This could be co-work scenarios, but also using this framework in education or in therapy. Now, possible applications in therapy could, for example, include children with physical disabilities, which is a project we've been doing here in Waterloo. It's the MSc project of Hamza Mahdi, who will graduate this term, where we created a new robot with a new design in order to assist children with specific physical special needs. And here we talk about the not only the diet of the child interacting with the robot, but also other children that could be present, but also other robots. So children with accessibility needs have a number of barriers to play. So for example, when you think about ball games such as basketball, children who are confined to a wheelchair and have upper limb disabilities, they might just physically not be able to play those games. But play, on the other hand, plays an important role in child development, not only for cognitive and social development and motor development, but also for social development. It's through play that children also develop friendships, they learn about themselves, and they learn about others. So here the research question was, how can we use a robot and design a robot to create joyful play sessions that facilitate human connection for children, regardless of their physical ability? So it was an inclusive approach where we targeted a scenario where a child with special needs can interact with other children, including typically developing children. So we did a co-design approach here as much as we could. It had to be done remotely since we started this work in March last year during the first lockdown. So we had to do focus groups and interviews with parents and children remotely, and then gain their insights on the robot. So this is the robot called MyJ, which we finally developed. It can also be customized with some accessories. So as you can see, the robot can autonomously pursue and pick up balls and then shoot balls. So we were very much inspired by the game of basketball, which is very popular here in Canada. So we also used some expressive features. We used lights to indicate the direction of movement, and we also used lights in order to indicate some internal affective states of the robot, so that you can see here. And as I said, it is not only the scenario itself was designed to allow either pairs of children to collaboratively control one robot, or as it's illustrated here, to have two robots, each of them controlled by one child. And then the goal is that the children have to remotely control the robots. So some behaviors of the robot are autonomous, but the general direction of the robot is being controlled by the child, and then they have to score goals. So this is just an illustration of the hardware and the mechanism to pick up these balls robustly, but also safely. So we looked at different sources of inspiration for the shell design. In particular, it should not have any sharp edges. We decided on a zoomorphic design, which is very suitable for children, and also considered other inspirations on using lights for feedback, for example. And so we went through different prototyping scenarios when finally we then arrived at the design that you can see here on the right, and children can personalize it, putting some ears on it or some eyes. Well, these are fake eyes, not operational eyes, but we were told by the parents and by the children that they would really like that, because it gives them the impression then that the child would actually own the robot if they can modify its appearance. And here you see just a sample use case, which we internally validated, but due to COVID-19 restrictions, we were not able to actually have this robot interacting with children with special needs. So we will make this design open source, both the software as well as the hardware design, so that anyone who's interested in having a robot that can play basketball has the potential to replicate that system. There are, of course, still many challenges that we need to consider here in terms of usability. And finally, hopefully later this year or early next year, we can get feedback from carers, relatives, and therapists. So now let's go back to some dyadic interaction, some projects we've been doing here, which is the MSc project of Puria Aleascari here in Waterloo. He has graduated actually this term, where we were interested in the scenario of a human teaching a robot. So let us assume a human has already been able to teach a humanoid robot. How would the person perceive the robot's behavior when the robot is then practicing those tasks? So we were very interested in kinesics, so in body movements and gestures of the robot in order to convey social cues to the human in terms of the progress of the robot's learning. So this is in the context of human-robot social learning, but because of COVID-19, we were not actually able to run that study in the lab. It was done remotely, so people were not actually teaching the robot, but they were observing the robot after they had taught it how the robot would practice that behavior. So the goal here was to make sure that the teacher, so the human teacher of the robot, understands the meaning of a robot's nonverbal behaviors while observing it perform previously learned physical tasks. And we were here particularly interested in terms of how do people observing the robot judge the robot's confidence, eagerness to learn, and attention to task. So we did a study here on Amazon Mechanical Turk, 2x3x4 mixed factorial design. We had two priming conditions. In one, we told the group of people in a between participant design, we told them that they now watched the robot right after they had instructed it. And the other group were told that the robot had already practiced it for a while. But then within participant conditions, we varied the gaze of the robot, either always looking at the teacher, always looking at the task, or combined mode. And we also had 3 different types of arm movements, low speed smooth movements, high speed smooth movements, hesitant movements, and jerky movements. So here you can see an illustration of these movements on the right, an example of combined gaze mode with high speed smooth motions, and on the left examples with hesitant motions and with jerky motions. So we had a variety of measures, but as I said, we were particularly interested in people's view of the robot's confidence, attentiveness to task, and eagerness to learn. Okay, so this was an Amazon Mechanical Turk study where we recruited about 200 people, and we got 167 participants. We got useful results. We did not find any effect of the priming, so at least in this particular study, it didn't matter so much whether people were being told how long ago the teaching took place. Probably the priming effect wasn't strong enough, but because of that, we then pooled the data. So just briefly, what are the results in terms of robots' perceived confidence? So we found that arm movement here was the only factor that changed the perception of the robot's confidence. In particular, with high-speed, smooth movements, the participants rated the robot significantly more confident, while hesitant motion could indicate a sign of uncertainty. Regarding eagerness to learn, we found that the combined gaze mode resulted in the highest perception of the eagerness to learn. So remember, combined gaze mode meaning alternating between looking at the teacher and looking at the task. We also saw that high-speed motions could significantly improve the perception of the robot as being eager to learn. So finally, with regards to attention to task, we found that when the robot always looked at the task, so at the manipulated object, it was perceived as more attentive to the task, which is not surprising. But high-speed, smooth motions improved the perception of attentiveness to the task as opposed to low-speed movements. So we did not find any effects of these two priming groups, as I already mentioned. We also discuss in the publication where we report on these results a fatigue effect that we observed because the participants saw a number of videos in this study that we had to do remotely. We also saw that as age increased, participants evaluated the robot to be more attentive to the task and as more proficient and as more calm. So we were first a little bit surprised by that, but then we hypothesized, well, maybe younger adults had more higher expectations of the robot skills. So they were maybe expecting more from the robot as far as its skills is concerned. Of course, the main limitation is that it was a remote study, which is all we could do during COVID-19. So we are planning now to do actual human-robot teaching experiments with the iCub, with the actual robot in our lab as soon as we are able to. So now let me talk a little bit more about assistance for healthy aging. I've already mentioned that this is one of the topics that I've been interested in, both in my lab in the UK as well as here in Waterloo. I just want to skip some of the slides for the sake of time, but just to raise a few issues here that we need to think about in this application area. We need to think about very carefully about the role this companion should have. Should it, provide cognitive assistance, physical assistance? Should it provide health advice? Shall it also help with social assistance, for example, encouraging contact with other people, or even helping with loneliness? We need to think about where this assistance for healthy aging takes place. Is it in a hospital? Is it in a care home? Who are the robots assisting? Is it just the older people, or is it also the nurses and family members and others? What role should the robot have? Is it just for one particular task, or is it for many? What functionalities should the robot have? Also, so for example, therapy, or should it be just cleaning or housekeeping, or just a health monitor? And decisions on all of these questions will significantly influence on the type of social robots that you choose and the type of social behavior that you give them. and also what are our ultimate motives in developing such systems. Is it cutting staff costs? Is it compensating for a lack of staff? Is it providing enhanced care, for example, due to the fact that the robot can be available 24/7, rather than just a person having a visit once or twice a day? So the final study that I just briefly wanted to outline is a survey that we did twice during 2 lockdowns here in Canada, one last year and one earlier this year, where we looked at more society's attitude toward social robots. And that was done with my colleagues, Mujan Ghafourian and Colin Allard. So we were interested in what are people's perceptions of social robots, and has this maybe changed due to COVID-19? Of course, we could not do a pre and post study. We didn't know that COVID-19 was coming, but we referred to some surveys that have been done in several countries, including the EU and other places, showing that sometimes people have some concerns regarding social robots. They might be concerned about privacy, but they might also be concerned about ethical issues, that these robots should not replace people, for example. So we did here an Amazon Mechanical Turk study where we recruited participants during these lockdowns in May, June last year, and in January this year here from Canada. And we did we used various measures in order to assess people's perception of loneliness, their personality traits, questions on how they perceive social robots, and also their demographics, and in particular the individual experience of COVID-19. So we wanted to see whether due to COVID-19 it affected people's perception of social companion robots, whether loneliness can maybe increase the likelihood that people might be open towards social robots and might want to buy one. We also wanted to investigate whether certain social cues, such as emotions, were perceived to be important for such a robot to have, and also the relationship of people's personality types regarding all of those opinions. So one result we found is that whether people reported a positive perception change of social robots during the lockdown or a negative one, any reported change positively and significantly changed the perception of social robots. So when we ask, what you can see here on the horizontal line is the perceived effect of how COVID influenced someone's life. So from negative, not effective, or positive. And both with positive and negative, we see that it increased the perception of social robots. We also saw that the social capabilities of a companion robot, for example, the ability that it can recognize someone or that it can show emotions, was found to be more important than the technical soundness of the robot, for example, whether or not it made mistakes. And regarding loneliness, we also found that the measured loneliness significantly affected the likelihood of people to buy a social companion robot. So it seems the more lonely people felt in that situation when they answered the survey, the more positive they were in order to have such a companion robot. Of course, there are many challenges. What I just presented were just surveys, and in many application areas, not just regarding the influence of COVID-19, but also when you think about therapeutic or educational applications, we need long-term field studies. And that's something we've done actually with my team at University of Hertfordshire, and we just finished and published that work last year, where we deployed a humanoid robot in a nursery school for children with autism for a whole year. And even after that study finished, for several more years, the school has still been using it. So that was a study where the teachers at the school used the robots, not the researchers. So it was a proper field study that we did, where we looked not only at the dyads, so the children interacting with the robot, but also the relationship of the staff and their interaction with the robot and their perception of the robot, and also factors at the organizational level. So here, this was done with the humanoid robot Casper, and we were interested in the acceptance and these different factors of technology acceptance that have also been discussed in the literature. So we visited that school 4 times, as you can see here on the top right, in different periods where we did interviews with the staff. We also measured and had the staff also completing questionnaires about the children's developmental levels, and in order to see in a pre-post comparison on whether the exposure to the robot had improved their development. So these are just some changes in developmental scores that we measured in terms of sensory abilities, communication, cognition, social abilities, and also motor abilities. So what we found here is that we really do not only need to look at the relationship or the interaction of the robot and the child, we also need to look at the staff, their conditions, their working conditions, their curriculum, how they have time to use the robot, how they value the use of the robot. So it is basically a very complex interplay of different factors related to the staff, to the children and their motivation and intention to use the robot, as well as available space in the robot to set up, space in the school, to set up the robot. So in this area of robot-assisted therapy for children with autism, many robots have already been produced and are being advertised in this particular area. But something that I always wonder about is where are these millions of robots that we want in people's homes and in schools, and that should help children? There's a lot of research studies giving very positive evidence that robots can make a difference, but we haven't really yet managed to get these systems out, to get these systems actually being used. Typically, it's just being done as part of a research study, and then at some point you finish the research study, and the question is then, what do you leave behind once you take the robot away from the particular setting? Okay, so for the sake of time, I just wanted to conclude with these questions. I'm also continuing here in Waterloo to work with children with special needs. As I mentioned, at the moment we have to do all of these projects remotely, but I'm looking forward to also work with children with severe physical disabilities, but also with other groups of children with special needs who can benefit from social robots. Okay, thank you.
Excellent. Thank you very much, Kerstin. Fascinating talk, and giving us lots of insights into fascinating, sometimes controversially discussed areas of robotics. So given we've unfortunately lost our audience, we could maybe briefly come back to some of the questions that were asked from the audience, but also a couple of questions that I would like to ask you. But looking at the audience chat, there was one maybe very simple question about Pepper and what's the Pepper controller?
Yeah, Pepper is a robot. I maybe should have mentioned that. It is not a name that we gave to the robot. It is being sold. It is a humanoid robot, and the controller of Pepper is just the programs. So I think that was part of the HRI PhysioLib study that I presented, and it was just showing that we interface that system with all of these different controllers of the different robots.
Okay, and the other question from the audience was around kind of the multidimensionality of the problem of what kind of qualities do we want to associate with human-robot interaction and human-robot conversation, if you like. Maybe.
Yeah, absolutely. I mean, quality of interaction is a multidimensional concept. No study can address all of these different dimensions. So what I showed you were just in this presentation some example projects where in one of the projects, for example, we use physiological signals in order to make the robot adaptive, in order to increase the quality of the interaction. In another study, we investigated cues and how they can influence in how people perceive the robot. But there are, of course, many other aspects also that would be important. I mean, I would say research on improving the quality of interaction in HRI is still at its infancy. There's still a lot that needs to be done, and it also needs to be addressed from a very interdisciplinary viewpoint, not just from a technical viewpoint.
Okay, then I've got a few questions, if I may. I think they're all fairly short, but one thing you mentioned towards the end of your talk was the benefits that education and children's education in particular might have from using robots. Now, you kind of alleged that we're far away from having robots in every household. But then my question would be, well, just putting a book into a child's playroom doesn't make them read. How is it with robots? Do you think just having a robot with a child will automatically have those educational benefits, or does something else need to happen as well?
That's a very important question, and I would completely agree with you. And there are actually studies that sometimes indicate that even if a robot is fulfilling its function, it doesn't necessarily mean it is influencing people's behavior or people's thought. And so I would, just to answer your question directly, I would say it is absolutely not sufficient to just put a robot in every classroom and in every children's bedroom on their desk. We need to really make these robots engaging. We need to improve the quality of interaction. We need to also go beyond the well-known novelty effect, the fact that in an initial encounter, people often are quite positive about having a robot, but then after a while it might get boring, which means we need to design these robots in a way that they can go beyond this first encounter, that they can learn, they can adapt, they can learn about the person, they can learn about, for example, when it comes to education, about the child's progress, on what the child is good at, what the child is not good at, what the child likes to do, and what the child doesn't like to do. And then using that knowledge in order to tailor the interaction to make them enjoyable. And if they are enjoyable, then the children would want to interact with the robot, and then the robot could succeed in order to achieve some educational goals. But it is certainly not as simple as, oh, let's just build a nice robot, let's make it affordable, put it into everyone's home. That doesn't mean that that robot would actually be successful.
Okay, thanks. Another question that came to mind was you talked a lot about children interacting with robots, but when you come to kind of dementia scenarios, etc., you'll have adults interacting with robots as well. Do you find there's some overlap of required or behavior that the human would like to see, regardless of whether they're a child or an adult? And are there distinct, different kind of sets of qualities or behaviors that you've found out in your studies?
There are generally certain aspects that all children and all adults would enjoy with a robot. They would enjoy a pleasant design, a robot that is nice to look at. If the robot affords touch, then certainly, having a nice touch could also make the robot attractive. There are also commonalities in terms of the social cues the robot can use. So creating rich and interesting multimodal interaction, I would say that applies to all application areas. But when it comes to very particular application areas and groups of participants, for example, children on the autism spectrum or children with physical needs or people with dementia, you need to look very, very carefully at the situation and the condition and what people actually need. So I'm reluctant to generalize. For example, what we've learned from studies with children to adults, in particular people with dementia, because I think this is a very different group of participants. We need to look very, very closely, talk to their carers, talk to clinicians, talk to the care staff, talk to them in particular. So I think with this, they are going back to your question, as I said, so there are certain common features of robots that can make them attractive to everyone. But when it comes to certain applications, you need to very, very carefully have this human-centered approach, this co-design approach. You cannot say, oh, but I did a study with children, let's just apply the same to working with people with dementia. No, people with dementia are not children. They are people with dementia. And because of dementia, they need certain considerations and there are certain requirements. And they are also people. You always need to look at the individual person. One person with dementia is not the same as the other person with dementia, in the same way, actually, as one child with autism is not the same as another child with autism. So you need to look at the particular condition, any medical, social, cognitive, physical requirements, but also at the individual. This is what human-centered approaches are about.
Yeah, so that makes it very, very complicated, not just having to look at cultural and community contexts, but really at an individual level with each human that is interacted with. Yeah, very interesting. Maybe last comment, you mentioned in several places how COVID and the situation has affected your research. Now, we've seen in other areas of AI where it comes to, say, multi-agent modeling and, say, use of machine learning for drug discovery or vaccine discovery in particular, we've seen AI flourish during the pandemic and the applications kind of amplifying. Now, it seems from what you said, you've seen this more as a hindrance to actually do that interpersonal or human robot interaction study, because you simply couldn't do that with the social distancing and lockdown situations. Do you see that kind of becoming better in the next few months, hopefully, and do you have any plans on how to accelerate that to make up with the lost time?
Well, we didn't necessarily lose time. We were quite busy, and we were able to complete research projects, write them up, have them submitted. This has basically continued as before. It's just my personal passion is about having actual robots with actual people in a room, and you know, make them together, solve certain tasks, communicate with each other. This is where my passion is, because this is where the most interesting things typically emerge. Things that you hadn't thought about before, that you hadn't thought about in your simulations, for example. This is where the real world interaction is really, really important. And I certainly miss that. But of course, I had to keep my research going. I had to make sure that students, MSc students, PhD students who started in my group before COVID-19 hit, that they're actually able to be productive, have publications, and graduate. I could not have just said, oh, sorry, now we cannot do what I really want to do. Let's just go on holiday for who knows for how long. No, that was not an option. It was not an option. We had to really think very hard how we can move all of our research online. Sometimes doing studies, doing co-design studies, or at least user-centered studies, but again, via Zoom. So at least there were actual people involved, but they could not come to the lab, or we could not bring robots to them. So I am looking forward to a time where we can actually go back to this in-person studies. But certainly in HRI, a lot of the studies that we were possible remotely, but it then remains to be seen how the results from those remote studies would then translate to in-person studies. So that will be one of the challenges, but it's not just the challenge I face. Every researcher in the human-robot interaction community faces exactly that same problem.
Yeah, of course. Brilliant. It's been fantastic chatting with you, listening to your talk, very insightful. So thank you very much for your time, and thanks for joining us this afternoon here, this morning for you over in Canada. Yeah, it's been wonderful, and please do keep in touch, and well, hopefully we can welcome you again soon to either an AISB convention or another talk or some other event.
Yeah, I would definitely love to visit the UK again. Last time I visited was in 2019, a couple of times, and I'm definitely looking forward again to visit. And thank you again for the invitation and everyone attending and asking questions.
Okay, thank you very much, Kerstin,
And
and
thank you.
take
Bye
care
bye.
and see you soon.
Bye.